So this evening's meeting is titled Chip Design. And one very important aspect of chip design is the verification. So I'm going to spend a little bit of time talking about verification, how it's done in the industry, kind of the direction verification is taking, and how it's possible to out-verify the pros using open source frameworks, of which I'm going to present one that me and my colleague Stu over there have created. And before I start, I just want to clarify what verification is. So it's effectively making sure that the design you've created is going to work. And in this context, we're talking about functional verification using simulation. Okay. Right. So verification is important. I hope that's kind of obvious. People say that a lot, but I think it's worth just pausing briefly before we start to explain why it's important. Obviously, if you fork out several million for a mask set for an ASIC, and then it turns out it comes back and it doesn't work, you'll think verification is important. But actually, this chap on the left, Byron Kernighan, said that debugging code is twice as hard as writing code. And actually, we've got a bigger problem with chip design because we have to design our chip. Then we've got to create some kind of test framework to verify it. We have to debug our chip. We have to debug our test framework. And it's the verification that kind of limits the complexity of what we can achieve. So a breakthrough in verification efficiency allows us to design more complex chips. And lastly, verification takes a lot of time. So there are some figures here from the Wilson Research study recently, which shows that verification, the majority of time of design engineers is spent verifying. And actually, these are projects that typically also have an independent verification team. So the majority of effort in producing any kind of chip is generally the verification. Okay. So verification is also expensive. So in the industry, you're talking licenses can be sort of $50,000 per seat per year. The engineering time is very expensive, so verification engineers are quite expensive to employ. You need lots of servers, you need equipment. If you've got emulation tools, you could be talking $500,000 for an emulation system. You need to train people up. Basically, if you want to design a complex chip in industry nowadays, you need to have very deep pockets. Okay, but lastly, and this is something that we're trying to address, is that verification is inaccessible. So there's not very much information available on the internet. It's a very niche skill. So most of the tutorials that are there are either far too simplistic, so they don't teach people enough. So it's very hard to, as a hobbyist or someone trying to teach themselves, you don't have access to the tools, you don't have access to good information. It's very hard to actually become proficient at industry level verification, just kind of from your home or as a kind of self-learning exercise. You can, of course, lock yourself in a room with the System Verilog LRM, the language reference manual. But System Verilog is a very complex language. You'll probably go mad. You'll see on Stack Overflow there are very few sort of questions relatively. So this is a logarithmic scale on the bottom. Relative to mainstream languages, there's very little help. And actually, if you look at some of the questions that are being asked, some of them are quite basic, or it's not a very good reference. So compared to trying to teach yourself something like Python or Ruby or C, the information just isn't there. Okay. So moving on, what do you actually get for your money? So if you're in industry and you're spending all this money, what are you doing? So the biggest thing that the sort of recent innovation, or recent in the last decade, which is recent for verification, is constrained randomization. So effectively, what constrained randomization does is allow you to trade CPU time for engineering time. So CPU cycles become cheaper, so it's a very good trade-off to throw CPU power at a problem and free up your engineers to do something else. What it means is we describe the problem in terms of a set of constraints. We use a constraint solver to solve that problem, and it generates stimulus that exercises our design. So a classic example of that would be Sudoku, where we can describe the problem as a set of constraints that have to be satisfied, effectively the rules of the game. We throw CPU power at it, and it can solve Sudoku for us. We can do the same thing with our tests. So we can describe what valid inputs are for the different interfaces, throw CPU power at it, and it writes tests for us effectively. If we're using constrained randomization, though, we have to combine that with functional coverage. So it's no good just throwing loads of stimulus at a design. You don't know how well you're verifying it. So functional coverage is effectively instrumenting your design to track what scenarios you're hitting with your random stimulus. So let's see, for example, you might have a functional cover point that says, I want to see this FIFO being read and written at the same time when it's full. Okay, so this is, I guess you guys are probably familiar with code coverage, branch coverage. This takes it one step further, where we actually have to effectively annotate our design with additional information that says, these are scenarios that we want to hit, and then we can track whether our verification is hitting those scenarios. Okay. In theory, if you've got a model of how the system should behave, and you've got cover points tracking how well you're doing in verification, then you can just throw CPU power at the problem, and you know when you're done. You just wait until you've generated every possible scenario that is interesting to you, and you've got a working chip, in theory. In practice, that's often not the most efficient way, so you combine some random stimulus with some directed tests. You want fast running regressions, for example, continuous integration, things like that. Okay, and building on constrained random and functional coverage, we have the UVM, the Universal Verification Methodology. So this is the biggest kind of event in the verification world at the moment. There's a lot of hype behind it, and effectively it's a toolbox of macros and functions written in System Verilog with the intention of making verification environments interoperable. Okay, and what you're actually getting when you kind of buy all this stuff is you're paying for a proprietary and buggy implementation of a committee-designed 10-year-old language, which is actually bolting software concepts onto a 30-year-old language intended for hardware. So I don't know, my bias might come through a little bit, but I'm not particularly impressed with what the industry's come up with to date. And in fact, I want to pause briefly on the UVM before I move on. In theory, UVM is an open source framework. In practice, I think it's actually an example of how the industry kind of views open source at the moment. So it's a very tightly controlled project. It's a closed committee, which you have to pay to join. Discussions are in private. If you want voting rights, so for example, if you actually want to influence the technical direction of the project, it's £25,000 to join the committee. There's no obvious way for people to contribute. They're not interested in offers for help. You can't even raise a bug as a member of the public. So it's like the old school open source, where a company kind of creates a big tarball full of fairly shoddy code, shoves it online and says, there, we've open sourced it. And then all these vendors come along, they download that tarball, they make loads of modifications that don't get fed back upstream to kind of optimize it for their platforms, and then they distribute a binary version of their optimized UVM. So it's kind of, I don't know, it's open source, but it's sort of lacking. But anyway, I'm going to move on because I could spend half an hour whinging. This is so inspired by the PHP double claw hammered hammer. I think this is the UVM hammer. It's a tool, it works, but it's not very efficient. Okay, so I'm going to move on and talk about Cocotb, which is it's an open source Python verification framework. It's been around for about a year now, but it's kind of gradually getting traction. most important point, it's not UVM. It's open source and it's Python. So why Python? Okay, no, how does it work? Why Python comes next. I know you're excited to find out. So how does it work? Basically, there's lots of very clever stuff in here. You still need a simulator, so it's not a simulation tool. You take your design written in VHDL or Verilog. It hangs in free space in the simulator. You don't have to write any kind of wrapper. You don't have to instantiate your design even. It just sits there in the simulator. We've got some C code here which abstracts the kind of, most simulators have a foreign language interface. We abstract that away so that we can work with lots of different kinds of simulators, different languages. We simultaneously embed and extend Python, and the Python interpreter runs in your simulator process. There's some Python kind of helpful stuff to make it easy to access your design. That's kind of pretty much it. If you're interested in finding out more, the source code's available, so you can look it up. So why do we use Python? So Python is accessible. It's a common ground for hardware engineers, software engineers, the verification team. Even like my 10-year-old nephew's learning Python. It's a point where all these different disciplines can come together and operate on the same code base without too much problems. You've also got rich standard library, lots of third-party modules. It's a very efficient language for writing stuff. Okay, it's fast enough. So we talk to quite a few people, and they often say, "Oh, Python, that's going to be well slow." I've actually done some micro benchmarks of Python against System Verilog in some popular simulators. And for example, a dictionary lookup in Python is 20% faster than associative array lookup in System Verilog in several simulators, or well, all the simulators I've tested. And actually, I think there's just this perception that Python is slow, but in our experience, it's faster than System Verilog for the tests that we write. And I think that's partly because Python's had a lot of effort gone into, it's a mature language, whereas when you buy a simulator, System Verilog, you're buying something that's proprietary and it's not as well optimized. It hasn't had nearly as many hours of CPU usage against Python. And it's fast enough for what we need to do. It's also a great glue language. So when you're verifying stuff, you might be talking to a model, you might be talking over sockets, you might be trying to emulate real hardware, you might be trying to interact with a Linux TCP stack or whatever, and Python's a great kind of point to drive all that from, so you can glue everything together. And of course, development speed is everything. So if you're trying to create a chip, the less time you spend on verification, the better, assuming your chip works. So development speed is everything, and Python gives us a great speed at which we can develop. Okay, so what does Cocotb look like? This is a kind of an anatomy of a test bench. I know it's always a bad idea to put code on the slide because no one reads it anyway. These are in the kind of, we've got tutorials and documentation on our website if anyone's interested. But effectively, we create a driver and a monitor for we've got some streaming interfaces here. We've got a configuration status register port here. We create another driver for that. We create a scoreboard. We create a monitor that recreates transactions off the stream in bus. And here in sort of 12 lines or whatever, we've created quite a complex test bench. So this is the structure we've just created with those lines. So we've got kind of something that sends transactions into our device under test, something that takes the transactions that come out. We compare them going through a model on the scoreboard. We also got something to set up configuration status registers. And I don't think you could describe that in a more concise form than this code. So that's basically what we've aimed for. You don't have to instantiate anything around your design. It's concise, it's quick. The other thing that's quite handy, so being Python, for example, we can create quite complex test benches that interact, for example, with Linux. So in this, this is a tutorial that's in our documentation. But basically, we've got a simple design that responds to pings. We create a test bench that uses the Linux TUNTAP virtual interface so that we can run ping in our terminal, and we ping our simulated piece of hardware. And we get not too bad response times. That's quicker than crossing the Atlantic. So and this whole example is 50 lines of Python. So we can do complex stuff very quickly. So it's great for sort of gluing stuff together. Okay, what about constrained randomization in Python? So there are a few open source libraries available. Probably the most promising one is the Google Operational Research Tools, which has a constraint solver written in C++, got Python bindings. I'm sort of playing with that at the moment. There's also a pure Python library called Python Constraint. Both of these, similar kind of things. But I mean, the point I'm trying to make is you don't have to spend tens of thousands of dollars to do constrained randomization if you want to use that as a verification technique. And there are plenty of open source tools and projects available that you can make use of in your verification. Okay. I'm going to make the point that we're probably not going to actually integrate a constraint solver into Cocotb. So I think it's probably better to just allow people the option of using whichever library they want to. But that's not true for functional coverage, which is something we're looking at the moment. So the nice thing about doing functional coverage in Python is that we can, using the same mechanism, we can track the coverage of our test and our test framework. We can take coverage off a model, which is usually a software model, and we can take coverage of our design under test. And we can do all this from within Python. So thankfully, after, I think, about 6 years of deliberation, a committee has come up with a standard way of defining coverage interoperability. A coverage model is very simple. It's a hierarchical set of counters. That's all it is. It took 6 years to come up with an XML schema for exporting that and importing that between tools, but we now have it. So we're looking at tracking coverage in Cocotb and exporting that using UCIS, which is this interoperability standard, which would allow you to kind of take coverage, merge it using third-party tools, or view it using standard, if you can combine coverage from different tools, etc. And we're working on the API at the moment, so if you've got any thoughts on how that should look, feel free to chime in on GitHub. Kind of looking at some kind of decorator-based sort of, I don't know, something neat. But if you've got any ideas or thoughts, do chip in. So kind of putting it all together, it's a random screenshot. So we've been kind of fortunate in a way that both myself and Stuart, we've been working on Cocotb for probably a year and a half. We've gone into a variety of companies and been able to persuade them to use Cocotb. And we've always seen an improvement in terms of both development, speed, and the quality of results. But it's also a kind of it's like it's a philosophical thing as well. So with Cocotb, we've gone for making it easy to write tests, so you can create a test bench for even the smallest piece of code. The overhead of creating a test bench is very low. We output test results in JUnit format, so it ties into Jenkins. You get nice test result trends, you've got a regression, it's triggered off a post-commit hook, everything works, test takes 30 seconds to run. And what we found is you go into a company, majority of chip design companies are quite kind of behind the times when it comes to continuous integration, using open source tools. And we've gone into places where they've got some hacky Perl system with hundreds of scripts that takes months of effort to maintain, and it's forever breaking. And we turn up and we can write, in an hour we can have a Jenkins setup up and running with a Cocotb test bench, effectively replicating what's taking them months of effort to achieve. So it's quite rewarding, because what we've done is we've worked in the industry for over 10 years each now, and we've seen kind of the good, the bad, and the ugly, and we've tried to take lessons from that and come up with something that is neater, avoid some of the pitfalls, and we believe it's more efficient and generally an improvement. Okay, so and you can do things, in Jenkins it's quite nice, you can track your coverage over time. I'd highly recommend using Jenkins if you're using Cocotb. They work well together. But in summary, I'll I'll wrap up. Verification. I mean, we have working chips in our systems, right? So it can't be that bad. I mean, we're all buying phones or whatever. They're quite complex. So stuff is, it works, but it's not great at the moment. Seen from the inside, there's a lot of room for improvement. And I think verification is ripe for an overhaul. And we see some progress. There's movements towards formal methods, graph-based test definitions, platforms that work in simulation, emulation on hardware. There is innovation. I don't want to get too hung up on, I think the industry is inefficient, but there are steps forward. But the bread and butter is pretty bad. So there's plenty of room for improvement. Also, chip design is growing, and I think this is a key thing. So you've got Altera and Xilinx both produce an FPGA with ARM cores on it. Intel have even announced a Xeon with an FPGA attached, coming sometime in the indeterminate future if it comes. But there's a trend towards closer coupling between FPGAs and software. More people are experimenting with FPGAs. So the chip design market, if you like, is opening up to a wider range of people, which is great. We've also got things like high-level synthesis, and FPGAs are getting bigger, so you can do more interesting stuff with cheaper FPGAs, and that trend is going to continue. System Verilog, which is the current state of the art, it's a bit like PHP. It's too popular to die elegantly, but it's if you're getting into chip design, you can gain a competitive advantage, and we've seen this commercially, not just for hobbyist projects, but you can gain a competitive advantage by kind of leapfrogging or avoiding the kind of common inefficiencies of chip design, which are kind of endemic in the industry. So you can do better than the pros. You just have to avoid kind of thinking like them to a certain extent. Because open source verification is feasible. So we've got Icarus, which is a brilliant open source Verilog simulator. It's currently Verilog only, but there are increasing numbers of kind of system Verilog features being added to it. It's very quick as well. It's faster than a lot of commercial simulators. You've also got GHDL for VHDL simulation. And there's a new open source VHDL simulator which looks quite promising called NVC. So there is kind of gradual momentum. And as we see more kind of software engineers becoming interested in chip design, I think we'll see a kind of a more sustainable open source mindset. We'll have momentum to actually be able to carry projects. Large open source projects will be able to sustain themselves. Okay, and that's it. Thank you very much for listening. Any questions?
Just before you take questions, could you say a bit about potential ventures and whether you're commercial or what sort of organisation are you?
We're a kind of crypto organisation. So we are. I'm here with my co-founder Stu, who's kind of hiding there in the front row. So we founded. We've been going about a year. We're kind of bootstrapping at the moment. Cocotb itself is a tool that enables us to be more competitive. So it's not our main product. It's just an enabler for us. We don't yet have a main product to announce, but but it's that. Yeah,
Okay.
That's who we are.
Yes, Andy.
Hi. So my question is why do low-level verification at macro scale at all? Why is there this resistance in the hardware industry to high-level languages?
So are you suggesting using high-level languages as a design language or as a...
So I'm suggesting specifying the language, specifying the design in a high-level language, which compiles down to things which are independently well-tested already and fairly composable.
I think there is a trend towards that. It's very slow. Generally, if you're doing kind of pipeline DSP type applications where it's numbers in, numbers out, and you've got some kind of algorithm in the middle, that works very well. If you're doing something stateful, it's quite hard. For example, if your stateful packet processing, you can use elements of high-level synthesis, for example, to compile a DFA table or something, but the system Verilog as a design language isn't actually all that inefficient. You can write quite concise code. I mean, people don't, but you can. The inefficiency is in verification. The high-level tool chain works very well for certain problems at the moment, but for a lot of problems, it doesn't give you enough of an advantage. And in fact, the code that's generated can't compete with writing the code in System Verilog in the first place. So I think the tools aren't mature enough yet for that. I mean, long term, obviously, we need a high level of abstraction, but for
One of the electronic drivers there, hardware is a lot older than the software industry, and we're not doing it like that anymore.
yeah.
Save me from the software industry.
Yeah, I think it's all about the tools. So if high-level synthesis at the moment really worked, people would, more people would use it. For doing kind of DSP, so for radar applications, number crunching, it is in use. And you've seen both Altera and Xilinx have poured a lot of money into OpenCL. And that's great for kind of DSP type stuff, but that's not. FPGAs and chips are trying to design a processor in a high-level language that compiles to something efficient. We're not there yet, so it's not going to take over until when you can kind of design a processor in a high-level language that can place and route better than a Verilog one, then we'll see high-level languages take over. But
okay, I think we're pushing. I think the next talk might actually also touch on high-level ways of specifying certain qubits.
So this has been a big gap in open source hardware design for a very long time. I applaud you for taking this on, making it accessible. One of the things I think this would go well with is Verilator, because that's actually quite fast, right, for synthesizable stuff. And one of the problems with Verilator is that you can't compile non-synthesizable Verilog, right?
yeah,
Are you compatible with Verilator?
I haven't tested it. So if it's PLI compliant, then yes. But
It's a C model that spits out.
It's a
isn't
C
it?
Yeah,
model. It's got a VPI interface, DPI interface C.
yeah,
And
Well,
C interface.
But it's
So-
a lot faster than Icarus.
we've got a big list of things to do, so we'll put that on the list.
One thing that's interesting is, have you engaged with the open cores community, for example?
Engaged a little bit, maybe. We took so one of the examples that's available on the tutorials is taking an open cores block. So there's a JPEG encoder in Verilog, which has a kind of abysmal test bench, and we kind of gave that a rework, and it's quite nice now. So we just kind of as an example of I think to be fair, the test bench was abysmal because the tools weren't available to create something that was better than what was there. But yeah, I mean, as I say, Cocotb isn't our main focus, so we kind of, it's not where we put 100% of our effort at the moment. So we promote it a bit, but
I was sort of going from the idea of getting the community to do your work for you, because there's
Well,
a fairly active community out there.
we get contributions. There are people using it and they're feeding stuff back, which is nice, but it's not self-sustaining by any means.
How much commercial purchase have you had?
We've not made a penny.
No, that's like how much involvement from industry guys have you had? And what do they use it for generally?
So there are quite a few. You can count them on two hands, but there are companies using it commercially.
Just